I think we can start now. Can people online hear me?
Yes.
Let's see if they can. Yes, that's good. Okay. So the first chapter today we are going to talk about is the Brownian dynamics. And has anyone heard of Brownian motion? Yeah, most people seems familiar with it. It was discovered by a botanist, Robert Brown, in the 18th century. And he discovered that small particles inside water were moving around. And it was not due to the flow in water. He actually sealed the water to verify that it was not due to any motion or like flow inside the liquid, but it was just due to the collisions between the water molecules and this greater particle. And this is here, you can see some, let's see how I do it. Here is some trajectories that are manually recorded by an experimentalist, I always forget his name, Jean Perrin. And he was kind of making this kind of manual recording of these microscopic particles locations inside the environment. And then he kind of made the first quantitative experiments on this kind of Brownian motion. But why do these particles move around the liquid? Yes? Collisions, right? They are constantly colliding with all the surrounding water molecules, and this creates this kind of random motion. And in order to understand Brownian motion, we kind of need to go back to the simplest case because it's easier to understand, which is random walk. So what is a random walk? Random walk is the simplest random walk can be thought like this. I flip a coin at each time step, and if I get heads, I go to one step to the right, or I don't know, I go one step plus one. And if I go tails, I go one step in the opposite direction. So what is the novelty in this motion? What does this system become immediately? This becomes immediately stochastic, right? What is the difference between stochastic and deterministic systems? Any answers? Yes? Yes, there is a randomness, which means that each time I realize the same experiment or the simulation or whatever it is, each time the system runs, it's going to end up in a different position. This creates kind of a randomness, and we don't really know for sure, for certainty, where this particle is going to have. This is my step distribution. You see that there is 50% probability that I take a step that is -1, 50% probability that I take a step +1. So which means that if I take n steps, I don't really know where I'm going to end up, but I can actually calculate do the math and calculate what is my probability ending up each position in the one-dimensional coordinate. And then, of course, if there is no bias in the probabilities of the steps, if I'm taking equal steps to the right and left, my average position will always be where I started, right? So in average, I won't really move from my initial position. If there were hundreds of people like me, and then all of them operate this random walk, after however many steps, all the time, the average position of all the people that play this game of random walk will be in the center where they start the motion, right? So that's why the displacement, average displacement, is not a good measure of a random walk or diffusion, because it's usually 0 if there are no drifts. Is this clear? But there is a measure that is very useful. That is the square displacement. What will be the average of the squared distance after I steps? Okay, and this is not very difficult to calculate. We can, maybe I can take this to, no, I didn't do that, sorry. Yes, I don't touch it again. So after one step, I have a 50% probability being at -1, right? And 50% probability being at +1. I put the variable here, x squared, I am averaging over it. I multiply by probabilities of each cases, I get 1. I mean, if I'm at -1, it's straightforward, right? My x squared is 1. If I'm at +1, my x squared is again 1. The average of x squared after one step is 1, right? And if you do the same math after 2 steps, you have a fourth of probability being at -2. You can get 2 tails and then go 2 steps to the left, or you can go 1 step left and then 1 step right, 1 step right and 1 step left, which both ends up in 0. So you have a 50% probability of ending up at 0, and then you have again a 25% probability that going to +2 after 2 steps, which if you make the math and calculate what is the average of x squared after 2 steps is 2. And if you do the math for 3, that you will end up finding is that that will be 3. But what we can do is that, of course, you can keep doing this calculation, but you can also, how do people? Okay. So let's say if we have actually it's better to do it here. So okay, so let's say I am looking for this average of xi plus 1 squared. Sorry, squared average, not the average squared. What this will be, I can expand this term, right? This is xi plus delta x. Let's say this is the step that I take in the I plus 1 step, right? And then I can take the square of this. This will be the average of xi squared plus 2xi delta x plus delta x squared average, right? These brackets, by the way, are a notation for an average. Also, all of those brackets. Okay. Here, of course, this is a summation of all the averages. I can take the terms individually. This is xi squared plus 2 times xi times delta x average plus the average of delta x squared. This we know is 1 for random walk. It could either be -1 or +1, right? And these ones is my delta x in the next step. Does it depend on xi? No, right? They are independent. So this has equal probability of being -xi or +xi. And also xi has equal probability of being plus or minus values. So both of them independently have 0 mean, which means that this term will disappear. What I end up is xi plus 1 square average is the average of xi squared plus 1. And you can actually, you don't need to do all this math. If you know the first one, we know all the rest. So we can see that for random walk, the simplest random walk, the after n steps, or yeah, we can use the same notation I, my mean square displacement will be I, right? Is this clear? Because the average square displacement of single step is 1, and this is adding up. Is this clear? This is a very important measure to understand, because we cannot, the mean doesn't give us much in random walks. Then we continue here. So now we are going to see something else, which is not quite straightforward to derive mathematically, not very difficult either, actually. I have my lecture notes from stochastic differential equations from a few years ago, and it's not very difficult. Maybe it will take a page or two to derive this, but no matter what your step distribution is, as long as you have the same, as long as you satisfy the same conditions that your step distribution has zero mean, all of them have zero mean, and the same variance, they will end up, if you take enough number of steps, if you take many steps, they will converge to the same kind of motion. The characteristics of the motion will be the same. So here what we present numerically is that there are three kind of random walk step distributions. First is the one that I told you about. You flip a coin, you go either +1 or -1 at a step. Second one, you have a Gaussian step. So you take a random number, just like the number you get from a random function in the computer, so which has a Gaussian distribution, zero mean and one variance. You have this distribution, and this is a third distribution that you can have, and it's also have so you have I think this one is the values are written in the lecture notes. So you have 30% of I don't remember, square root of 3 + 1 divided by 2 or something like that, and then these two. So this is you see that these steps are asymmetric, like these two are symmetric, but this distribution is asymmetric. It doesn't even have to be symmetric, but these still have mean 0, their average is still 0, and their variance is still 1. So I satisfy that, and I run all of them for 1,000 steps. You see here are the steps, and I here plot 100 trajectories for each. Here we see immediately that each motion is ending up in a different place, right? After 1,000 steps. You see that every trajectory is unique. So this is why it's very important to know the averages, because we don't really know what individual trajectory is going to yield after a certain time step. This is the fundamental difference between stochastic systems and deterministic systems. In a deterministic system, you have forces, you have initial conditions, right? You start from a point, you know where you are going to end up. In stochastic systems, each time you start the same point, you are going to end up in a different place. Of course, what you can calculate is the probability distribution, right? What is the probability distribution? I will be here after 1,000. What is the probability? I will be here. I will be here. And you can show that even the step distributions are different, since they share the same universality properties, such as the zero mean and the one variance. At the end of 1,000 steps, their distributions will look identical. I mean, maybe they are not absolutely identical, but that's because you can blame the time steps. 1,000. If you take more steps, they will look more and more identical. Of course, if you take a few steps, they will not look at all identical, because the step distribution is totally different. But if you take enough steps, they will all look similar. So this is important. And this is why it actually doesn't matter if you are taking Gaussian steps or +1, -1, for example. If you take in enough steps, or if you take in the time steps small enough in your simulation, it can actually give you the same results. Okay. Is this clear? Any questions? Let me check here. No? Okay. So the next thing I want to talk about is the simulating for small time scales, or determining the time step of the random walk when we simulate it. So, okay, in stochastic diffusion equation, we have a derivative of x, right? That is changing randomly. Here, w is a random term, okay, that represents our stochasticity, so randomness in the system. So what I can represent this in a system is that xi plus 1 is equal to xi plus wi times delta t, which wi here represents the random number associated with each time step that is deriving the particle. I am trying to model the system. This is reasonable, right? So each time step, but what I end up with is that what is the square displacement of this time step? It is wi, let's say these numbers, random numbers I generate, have variance sigma squared w, okay? This is something, a random number generator I use, or anything like that. And let's say they have a variance sigma squared w. If they have this variance, the mean square displacement at each time step, if you do the same math that I showed you here, you're going to find out that each time step, your mean square displacement is going to increase by this much. Okay? And at n steps, if you run the system for n steps, this is the mean square displacement you are going to have after n steps. Is this clear? Yeah. And what you can do is here, we do a very important replacement. I can replace n times delta t by t, right? That is the amount of time passed after from the start of the simulation. So now I have a mean square displacement of the particle after n steps. This is something that is associated with my random number distribution, the variance of the random numbers I give. If it's Gaussian, it's actually 1. It's not very relevant here. And I have the time. And I have the delta t. I really don't like this. Why? This term bothers me so much here. Why does it bother me so much? Yes. Yes. The output of the system each time is going to depend strongly what delta t I choose. Is this clear? I mean, a simulation should not, the results of a simulation should not depend very strongly on delta t. And this doesn't matter if delta t is small or large. I can choose it very small. Still, if I choose it smaller, it will yield a different result. Is this clear? So that's why when we deal with stochastic differential equations, especially when we treat them numerically, this is important that we have to scale our random number according to what delta t we use. How can we get rid of this delta t? We can scale our random number with wi divided by square root of delta t. So that the variance of the steps here, wi is just a Gaussian number with mean 0 and variance 1. Okay? Round n, if you want to think of from the programming perspective. If I scale like this, what will happen is that my mean square displacement, since this number will scale with 1 over delta t, this will cancel each other, and mean square displacement after n step will always be scale with t, and that won't depend on delta t. Is this clear? So if you put this equation, this difference equation here, the big W, if I replace with this one, here small wi is just round n if you're numerically writing it, okay? It's round n, nothing else. So it's a Gaussian number, Gaussian distributed number, random number with mean 0 and variance 1. And you, instead of delta t, since we are scaling the noise by 1 over square root of delta t, this is gonna now become, there is also 1 delta t here, this will cancel half of the power here. This will be wi square root of delta t, okay? This is how we simulate the difference equation for diffusion. Is this clear? This may not be super clear, but do it numerically, and you will see super clearly that this is the case. If you treat the equation like this, when you program it numerically, the results won't depend on your choice of delta t. And here are some of the results. I simulate this simple, very simple equation. At each time step, I take a random Gaussian number and multiply by square root of delta t and sum over many steps. And I run the system for the same amount of total time, which is 5 seconds here, you see. But of course, the number of steps are very much different. If my delta t is 0.1, how many steps do I have here? 50, right? Here I'm simulating 50 steps. Here I am simulating 100 steps. Here I'm simulating 500 steps. Delta t's are different. And these are maybe, I don't know, 50 or 100 different realizations of the trajectories. You see that characteristically, they all scale very similarly because I treated my equation right with the counting into this time scaling of the random numbers. Is this clear? So this is important that we scale this noise with this term whenever we deal with stochastic differential equations numerically. Okay. And you can also see that there is in the lecture notes, there is the mean square displacement for all 3 cases. And you will see that all of them are equal. Yes. Try. It will look like this one. they are going to displace a lot larger than these ones. The displacement is going to increase. Overall displacement of the particles are going to increase with larger delta t. And it won't be consistent. Whenever you change your delta t in your simulation, you will get different results. This is something we absolutely don't want. And this is not due to the fact that delta t is large or something. Even if you take delta t infinitely small, very, very small, and then you change the delta t to half of its value, all the random displacements will decrease to their half. This is because the mean of the motion is 0. What you are adding up is if you take two random walk steps and add them on top of each other, what you are adding is the square displacement, which scales linearly with time. Normally, what you add up with motion, with simulating differential equation, is motion, right? Which scales uniformly with time. So displacement scales uniformly with time, with normal motion, but with random motion, the displacement square scales linearly with time. That is why we have to do this kind of accounting. And this is something, if you struggle, at the time I first saw this relation, I just didn't understand it. I was like, it didn't make sense to me. And I went there and programmed it. And when I saw that I have to do this to get them all consistent with each other, okay? I highly recommend try doing it. Okay, now we go to Brownian motion. This is the real physical Brownian motion. Of course, there are quite a few terms here, but the essence of the equation is actually the same. Actually, this one is very, very similar to the diffusion equation, but let's ignore this one first. We go from the beginning. So what we have here is I have a model for a particle inside the liquid environment, which is the acceleration of the particle. This is the inertial term. What is this term? This is velocity, right? The derivative of x. Yes. Friction, right? This is viscosity of the liquid environment. If I'm going with a velocity in one direction, I will experience friction forces. It can be air, liquid, whatever. And here is a term. I will come back to this one. This is related to the medium and the viscosity of the medium and the temperature of the medium. But this is something related to the diffusion coefficient. I will talk about this in a second. And we have our random term here again. Okay, this is the differential equation. And why do we have this term? And if you are interested in where this term comes from, this comes from the fact that the energy that is that my larger particle in the liquid environment, where does the energy come from? Why my particle moves in the liquid environment? It is colliding with other molecules, right? So it's the energy that comes from the other molecules, right? Because they are colliding with, and that energy that it borrows from this environment, it has to go back to the environment because it is also subject to friction in the same environment. So the energy the particle gets in average from this environment has to be equal in average to the energy it gives back to the environment with this friction, which is called the fluctuation dissipation theorem. Okay, it's just a conservation of energy at a statistical level. This is something that Einstein, this term is something that Einstein first derived. Okay, but this is just a constant that is related to the viscosity of the environment and the temperature of the system. Okay, it's just a constant at the end. So how do we deal with this numerically? I apply the derivatives. I take the second derivative of x. I have the mass. I have the particle velocity here. And I have the random term here, which has to be scaled by 1/square of delta t, as I just told you in the previous example. Okay, and you can do the math and you can calculate what is each time what is going to be my next step. Of course, since this is a second order equation, you don't only need the term before, but you also need the term 2 steps before to calculate the current step, right? But of course, if you think about it, for a certain system, all of these are constants. So this is a constant. This is a constant. And this whole thing, even you can take the, if your delta t is constant during the simulation, this whole thing is a constant. So it's essentially a constant time x I minus 1 and another constant time x I minus 2 and another constant times Randan. Okay? So it's not very complicated. It's just important to put all the constants right, that it works correctly. This is called the inertial, this is simulating the inertial stochastic differential equation of a Brownian particle. Okay? So we take into account of the mass of the particle. Is this clear? Yeah. Okay, in most cases, this equation becomes not very relevant. Can you imagine why? Or does anyone know why? We don't really need to simulate the mass of a Brownian particle. Okay, I can help you with what happens if I have if I jump from a plane with a parachute. As soon as I open the parachute, what will happen? The friction that is coming from the air due to the parachute is so high that I will immediately reach to a terminal velocity, right? According to the force I am applying down the ground. So I will going down kind of with it, if there is no wind and everything. So we are kind of simplifying the problem. Here, that's what's exactly happening. You think about a real person swimming in a pool, right? In a pool of water. And that is not at all the case for these Brownian particles. They have so little mass compared to their volume, so little mass that these terms becomes negligible in most cases. This is because they are kind of trying to swim. If you are a human, you can think about it like trying to swimming in a pool of honey. It is because you don't have any inertia there, because what I mean to say is that this term is going to be 1 over this term, m divided by gamma, is the characteristic time scale of the velocity relaxation for these systems. Because if there is no external force, this is how the velocity is scaling over time, right? Exponentially with m divided by gamma, with this time scale. And this time scale is in the order of microseconds. And the relevant time parameters for any simulation, any real world simulation for this kind of particles is seconds or milliseconds. So this becomes these terms become extremely small. That's why you can actually ignore these terms. And what you end up with is, you end up with this equation. If you kind of ignore the m from the beginning. Does this at least make sense? Yeah, okay. So this is called an overdamped Langevin equation. Okay, I mean numerical version of the overdamped Langevin equation. So we take the xi, we calculate it from the previous value plus a random value, Gaussian distributed, and this coefficient, which is the diffusion coefficient we have. Okay, is this clear? So this is very straightforward to calculate. You can see that this depends on temperature, the time step I choose. Of course, this is due to this normalization I was supposed to make, and the friction, the viscosity of the liquid. And I can show that these two equations are identical to each other at longer time scales. And here is a simulation. Here, the blue lines are the ones that are taken into account of the mass of the particle. At solving, they show the trajectory that resulting in solving the full equation with including the mass. Okay, this equation. And the dashed black line is the one that is solving the equation like this. I screw m, I take this 0, and I solve this part of the equation, and I get this solution, and I solve numerically this one instead. And I compare these two. Of course, if you are comparing, here tau is 0.6 microseconds, okay? if you are in sub-microseconds regime, where the particle is not even moving a nanometer, so it's a very, very, very small displacements and time scales we are talking about here. The difference is big. We are simulating something very wrong, of course, because in these time scales, when the delta t is very small, m matters. Okay, but when delta t becomes large, this term, you see all the scalings of this equation, right? Here, this term scales with 1 divided by delta t square. And this is relevant, this term, when delta t is around microseconds or smaller. Okay, as delta t approaches to milliseconds, just this term just becomes way too small and disappears. And that is why there is a big difference if you are simulating this system in very small time scales. But if you are simulating this system in 100 tau, this is maybe around 0.06 milliseconds. And even then, you see that the trajectories look very similar to each other. You see that the black ones and the blue ones almost overlap. And you can also calculate the resulting trajectories, mean square displacements. And you end up finding this one. You see that for small tau, for small time scales, the result that approximation we make with ignoring mass is not valid, because we see here that our result is not wrong, because we know for sure that the blue one is the correct one, because we take into account the mass. But if we ignore the mass, if our time scales are large, for about 100 tau time steps, the mean square displacement values are exactly identical, and the behavior. So if we are at larger time scales, we don't need to simulate this complicated equation. That is the conclusion. And we can just simulate this one. And this is also mathematically valid. Also in like entire soft matter science is developed upon this, also analytically and theoretically. A lot of people, when they simulate systems, if they are talking about experimental time scales, of course, these can change depending on the conditions. Under which conditions this can change? Under what condition does this approximation become less valid? Any guesses? Low viscosity, yes, absolutely. If I'm going to air, low pressure environments, people are creating experiments with atoms, right? Or very tiny particles in vacuum. What they mean by vacuum is never actually vacuum. A vacuum is standardized by the pressure, right? They decrease the pressure so much that the number of molecules in the environment that are colliding with my particle is really limited. What this results in is a very small gamma. When the gamma is very small, these terms becomes a lot smaller. This term becomes a lot smaller, right? This means that this term, compared to these two, which include gamma, become relatively larger and more important. And it becomes more important to ignore the mass. Or if I have a bigger particle, if I have a particle that is as big as millimeters, maybe it's not the best idea to ignore the mass. But as long as you go in the micro scale, this becomes not relevant for the time scales of relevant experiments, let's say. But of course, people have measured the velocities, instantaneous velocities of Brownian particles in nanoseconds. And they have confirmed actually that this equation is also like, we have to follow this equation if we are talking about very small time scales, okay? All of this makes sense so far? Okay. So the last part is I want to talk about in this lecture is optical tweezers. Has anyone heard of optical tweezers? You might have heard of it, particularly because it has received a Nobel Prize. I think it was 2 years ago or 3, could be 3. What is optical tweezers? Anyone has an idea? Yes. Yes. Why does that happen? Yes. Why does refracting light creates a force? Momentum. Yes, because the light has momentum, right? And this was first discovered in comets, actually. When people were observing comets, they observed that their tails were pointing away from the sun in astronomy. And they didn't understand it at the time, the reason behind this. But the reason behind this is what's called the radiation pressure. What this means is that if I hold a mirror with my hand, okay, I have not a mirror, I have a plate in my hand, okay? Someone is throwing a baseball ball. And then I am blind, I don't see the player because I am holding a huge plate, I don't see anyone. But whenever, and I am also deaf, I don't hear, okay? But whenever the ball hits the plate I'm holding, am I going to feel it? Yes, right? Because the momentum change of the ball is going to apply a reaction force onto my hands because I'm holding it, and I will feel the force. But if I hold a mirror against the sun, am I going to feel it? Whenever it's sunny, it's sunny. If I'm blind, am I going to feel the pressure coming from the sun? This is because the momentum of light is very small that it doesn't make a difference for me. It does make a difference for a comet just because its area of its tail is so large that the radiation pressure becomes relevant. But it also, this momentum of light can be very useful at micro scales. The reason is, why can we use this with microparticles so effectively? What changed the ability? What enabled optical tweezers? What is the technology? Lasers, right? They can focus so much power, light power, in a microscopic area. We are talking about an area that is maybe a micrometer square. And you can focus a few, like hundreds of milliwatts in that kind of area using a standard green or infrared laser. What this results in is that if I put a particle and I assume that I am focusing my laser beam with a high numerical aperture objective, what will happen is that each beam that is reaching the particle is going to be refracted by the particle, okay? And you are going to see that this is just a simple simulation, and oh, no, I cannot work it. Okay, we just watch it. So if you just think about it, if my particle goes down, the more beams will hit this side of the particle, they will be refracted more downwards, right? The light's momentum will change more down, and it will, as a result, if it goes down, it will be pushed up. You see the value of the force acting on the particle here. And if it is going too much in this direction, since it's like acting as a lens that is collecting the particle rays, and they are making them more straight, their momentum increases in this direction, which results in a force that is acting in the opposite direction. If it's getting too close to the beams, then this particle will diverge the beams in these directions more, and this will decrease the light's momentum in the propagation direction. This will result in a force in the opposite direction. And if you have a high numerical aperture objective, you focus highly focus a laser beam with high power, you kind of trap this particle inside the liquid environment, or air, actually. It doesn't matter. You can do it both. And this was a revolutionary discovery from Arthur Ashkin, and this was done in 70s. Actually, the first idea was not like as complicated as this. They discovered something much simpler. The first thing they discovered, but of course, science doesn't work like that. I mean, someone doesn't come up, I mean, it may happen, but someone doesn't come up directly with this idea. They first discovered this. They have a huge particle, and they have a very strong single laser beam, okay? They discovered what will happen to this laser beam. It will be refracted like this, right? What will happen to this particle? It is acting as a mirror, more or less, that is reflecting this beam, right? There is a resulting force in the opposite direction acting on the particle. This will eventually go up and align its center with the laser beam. Is this correct? So this is what people, of course, once it aligns, it will still keep pushing the laser, because some of the light is always refracted back from its surface, which is the radiation pressure. It will still keep pushing the particle in one direction. But what they did was, okay, then we can have one beam like this, another beam propagating from the opposite direction, and we are trapping a particle, microscopic particle in 1D. And then they did it in 2D, and then Arthur Ashkin was smart enough and wait a second, instead of doing this, if we highly focus a laser beam, these can kind of act as counter propagating beams, and this can trap a particle. And this is a very, straightforward tool to use, and this is a video directly from my lab. So here what I'm doing is that I am filtering out the laser beam so you don't see it, but there is a laser beam that is driving this particle around the liquid environment. As I move the laser beam, you can program this anything you like, and this is a microscopic particle. We can also trap bacteria or any kind of cells that is at the micro scale, things in air, everything. And this has been scaled to a lot of different things over the last few decades. Here you can see an example of optical trapping regimes. People can trap atoms, individual ions, quantum dots, viruses, biomolecules, all the way to algae and synthetic collages. That was the example I was showing in the previous video. Graphene, bacteria, anything that you can think of. People can do nanosurgeries on single cells using optical tweezers. It's a very advanced tool, and that's why it has, it has revolutionized soft matter physics with all this, enabling all these different kinds of experiments. So if you are interested, I highly recommend you can look up. It's Giovanni's book, Optical. It's one of the, I think there is not a lot of books on optical tweezers. This book was written obviously before the Nobel Prize, so before it was super popular. You can have a look at this book if you are interested in optical tweezers and its applications. So what happens if I trap a particle inside an optical trap? This is the last example for simulating Brownian dynamics. It becomes a little bit more interesting because I have this, before I didn't have this term in the middle. I had this one and I had the diffusion, right? What I am adding is an optical force that is pulling the particle back to center if it is displaced from the equilibrium, which is a linear force that is increasing linearly with this displacement from the center. Is this clear? It's kind of a stochastic harmonic oscillator. Of course, this particle is never going to oscillate because of the friction that is being, it's highly underdamped. That's why this equation is called underdamped Langevin equation. Do you have a question?
No, but why is it linear if it's like a harmonic oscillator?
What is linear?
Why is it linear if it's like harmonic oscillating? Because then it should be square, right?
No, the potential is square. The force is linear.
Yes.
And this is, why do we divide this by gamma? If you apply a certain force, the particle will reach to a kind of limiting velocity in a highly viscous environment, that its displacement will be proportional to force divided by the friction, right? So this is where it comes from. And we, of course, multiply by delta t because it's proportional to time step. And then what we can end up is that we can simulate this. For example, this is a simulation in 2 dimensions of a Brownian particle in an optical trap, where we have different stiffness in K for different directions. So you can easily see that here, this is X, this is Y. In which direction the stiffness is higher? The K value. This is a simulation in 2 dimensions. In X, I have Kx. In Y, I have Ky. Which one is higher, Kx or Ky? Any answers? Kx, right? Because it's stabilizing the particle more along X than Y. Particle is able to move more freely around Y than X. Okay? Let me just check if there are any questions there. No. Okay. Of course, once I know this, I can then further make calculations and verifications that my models work. What are the verifications that I can make? There are lots of analytical calculations that can be done and has been done on particles in microscopic particles in potential energy environments. And one of them is, of course, the Boltzmann distribution. I can check that if I have the energy, right? If I have Kx and Ky, the potential energy here is 1 divided by 1/2 Kx x squared plus ky y square. I can check the distribution in 2D if it follows the Boltzmann, or I can check individual dimensions. What is the distribution of y? What is the distribution of x? And I can check what it should be. It should be, I can maybe write it here. Or proportional to, let's say, e to minus 1/2 kx x squared divided by kbt, right? This is the Boltzmann distribution, and it should follow this distribution. And I can verify that. I can also verify the position of the correlation functions according to their theoretical predictions. This is something that the position of my particle inside the optical trap is decorrelating with itself with a certain time scale. And this is this time scale also scales with the stiffness value. The more I confine the particle, the faster it vibrates or fluctuates inside this trap. And this results in different time scales, you can see. And this can also be fitted. And also you can make what is the average variance of the particle trajectory inside this trap. And this one is actually a one-dimensional result. You can see that this is scaling with 1/k. And you can make the numerical experiment with changing the stiffness of this trap and repeating the trajectories a few times and then trying to see this behavior. Is this clear? Yes. What do you mean? This is a correlation, autocorrelation function for x trajectory, like x first dimension, and the autocorrelation function for the second dimension. You see that the correlation is decreasing slower for the y trajectories, right? The reason is that y is green. The reason is that it's moving more along that direction naturally because the stiffness is smaller. Think about the harmonic oscillator, standard mechanical harmonic oscillator. As you increase the stiffness, the period decreases, right? It is the same thing, but here the particle is not going back and forth like a pendulum because it's not really it's not an underdamped motion. It's highly overdamped, so the motion is totally random, but the effect is still there. If I increase the stiffness, the correlation, the particle's position will decorrelate with itself faster. Okay. This can be done by analytically shown by solving the Fokker-Planck equation for one-dimensional optically trapped particle, which is not very complicated. But these, at least the formulas are written in the lecture notes. And if you can go down to one of the references, it's called the simulation of a Brownian particle in an optical trap. And you can find more details there how these formulas are derived. And of course, you need to know, in order to reach this kind of equilibrium distribution, how long you should run these simulations, right? What is the overall time you need to run these simulations? This is an important decision. And what do you think would be a nice time scale to run these simulations long enough? Sorry? Yeah. Which means that it's depending on k, right? What is the natural characteristic time scales of this system? It's determined by this number, right? I mean, not if I put the k under gamma, the second term becomes xi is, or let's say, let me rephrase like this. What is the average of this term? 0, right? The only thing that has non-zero average is this term in this equation. So the average of my time step is proportional to delta t divided by gamma k, right? Unlike the standard diffusion equation, here I have a limit on delta t because I need to choose it a lot smaller than this. So it's not very close to the characteristic timescales of the system. So my delta t is not super large. Here, my idea is that delta t should be smaller, significantly smaller than gamma divided by k, which can be 10 milliseconds, 100 milliseconds, depending on the stiffness. You can see here the timescales I'm talking about, under what timescales it's decorrelating with itself, okay? And how long should I run the simulation is, again, a good overall time that I should run the simulation to get to an equilibrium dynamics is taking the total amount of time elapsed much larger than gamma divided by delta t. So if here, for example, it's something that I think this time scale is the time where it decreases to 1 over e of its original value. So it's somewhere here, maybe for this one, I can guess somewhere around 120 milliseconds. So maybe I should run it at least for a few seconds to get a result that I can rely on. I think this was the last slide. Yeah. Any questions about this lecture, Brownian dynamics? Let me see the chat. No? Okay, then we can have a break, and after the break, we can have a look at the anomalous diffusion.